I don't believe in a God. We don't even know whether the universe had a beginning. We don't know how it got hot and dense.
In the realm of cosmology, few questions are as fundamental and captivating as the origin of our universe. Renowned physicist and science communicator Brian Cox delves into this profound query in his exploration of why did the Big Bang happen? This inquiry takes us on a journey to unravel the mysterious origins of our cosmos as we seek to understand the forces and conditions that set the stage for the universe's spectacular birth. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space and beyond, consider subscribing. How did the universe begin? Scientists, particularly physicists and biologists, harbor a profound curiosity about the foundational aspects of life. They seek to understand the origins and evolution of life on Earth, a planet teeming with a remarkable array of diverse organisms. From the perspective of a physicist, the quest involves tracing back to the very inception of the universe, striving to paint a comprehensive picture of its origin and development given our current knowledge. A remarkable milestone in our pursuit was the recent, extraordinarily precise measurement of the universe's age, now determined to be 13.75 billion years old. According to this understanding, the universe commenced its existence 13.75 billion years ago. However, the why of this beginning remains a tantalizing mystery, and questions about what transpired before the Big Bang continue to baffle us. While these queries are subjects of ongoing research, our knowledge indicates that the universe was once intensely hot, dense, and inconceivably small. In fact, everything we observe in the present-day universe, from stars to planets to DNA to human beings, was at one point compressed into a space likely smaller than an atom. The universe's subsequent expansion and cooling led to the formation of complex structures, initially crystallizing out of the primordial energy. We have gained a remarkable level of understanding regarding this process. It is fascinating to consider that from that initial ball of energy 13.75 billion years ago, we have evolved to the present state, where we have galaxies, stars, planets, and life. To unravel the mysteries of the universe's origins, scientists employ multiple approaches. One way involves gazing skyward at the stars, while another entails constructing machines capable of recreating the conditions that prevailed close to the Big Bang. The concept that the universe originated from an unimaginably minuscule point and expanded to its current vast dimensions is both awe-inspiring and supported by compelling evidence. As Neil deGrasse Tyson eloquently stated, the universe is not obliged to conform to our comprehension. Two pivotal scientific discoveries lend strong support to the Big Bang theory. Hubble's observation in the 1920s of the relationship between a galaxy's distance from Earth and its velocity, and the discovery of cosmic microwave background radiation in the 1960s. When scientists discuss the expanding universe, they refer to its continuous enlargement since the moment of the Big Bang. Notably, this expansion does not pertain to the growth of galaxies, stars, or planets in terms of their intrinsic size, which is governed by fundamental forces acting on atoms and subatomic particles. These forces have remained constant. Instead, the expansion primarily manifests in the increasing distances between galaxies as space itself undergoes expansion. This prompts the intriguing question: what is the universe expanding into? Expanding the universe. The conventional explanation, as far as our current understanding goes, is that the universe's expansion isn't into anything external because it encompasses space itself, including space-time, as described by Einstein. To conceptualize the Big Bang as an event within pre-existing space is an inaccurate perspective. Instead, it appears that space and time originated at the moment of the Big Bang and have been continually stretching since. This is closely linked to the question of where the Big Bang occurred. It wasn't confined to a specific location within the universe because, to the best of our knowledge, all the space we observe was created during the Big Bang. Therefore, it occurred everywhere simultaneously. In essence, it did not expand into any external entity, although this concept can be challenging to grasp. It's worth noting that the foundation for these ideas lies in Einstein's theory of general relativity, which he formulated in 1915 and remains our most robust framework for understanding space and time, underpinning these intriguing and unconventional concepts. Singularity. When we apply the principles of general relativity to trace the expansion of the universe backward in time, it leads us to a point in the finite past where we encounter an infinite density and temperature. In the realm of physics, a singularity represents an incredibly minuscule space wherein resides an infinite intensity of gravity and density. To emphasize the gravitational force within a singularity is so overwhelmingly powerful that not even light can break free from its grasp. Parallel universe. Within a singularity, the Big Bang represents the ultimate extreme. In simpler terms, the entire universe was compressed into an infinitesimally tiny space. This compression, in turn, gave rise to infinite levels of temperature, density, and pressure. While these concepts may seem counterintuitive and bewildering, they rest on a solid theoretical foundation rooted in our understanding of the laws of physics. As previously mentioned, our natural instincts and perceptions, which evolved in the African savanna, struggle to fathom the concept of infinite density. However, even more astonishing and peculiar ideas abound. It's conceivable that our universe is not unique. There could exist parallel universes beyond our own. To illustrate this, consider a scenario where we exist in a three-dimensional space. Now envision a different setting where we reside on the surface of a two-dimensional sheet and the fundamental forces of nature, such as light and the strong and weak nuclear forces, operate exclusively within this sheet. Now, consider the possibility of another sheet, another universe, floating just a minuscule distance away from our own. You wouldn't be able to perceive it because light and forces are confined to our sheet. However, if this scenario holds true, we might attempt experiments to detect it, although the specifics remain somewhat speculative. Certain signatures of these additional dimensions, as they might be, could potentially be observable at the Large Hadron Collider at CERN. It's a realm of science filled with uncertainties, but the notion that another universe could exist merely a hair's breadth away from our own, extending infinitely in all directions, is a truly remarkable and mind-boggling concept, and yet we remain oblivious to it because the forces that govern our existence do not cross over to the adjacent sheet. Conclusion. Proving the existence of other universes would be incredibly hard, maybe even impossible if they don't interact with our universe in any way. However, if we have a highly accurate theory that explains how our universe works and also predicts the existence of other parallel universes, we could reasonably conclude that they exist even without physical evidence. To someone who isn't a scientist, it might seem like physical cosmology is making up stories without any real proof, but that's not the case. Take the example of the Big Bang theory. When it was first proposed in the 1920s, even Einstein dismissed it, but as the 20th century progressed, evidence started to mount. Astronomer Edwin Hubble in 1924 observed that the farther objects in space were from us, the faster they were moving away. This became known as Hubble's law and allowed scientists to estimate when the Big Bang happened and how old the universe is. In 1964, researchers discovered the cosmic microwave background radiation, which is the afterglow of the Big Bang. This provided undeniable physical proof that the Big Bang occurred. Since then, theoretical physicists have created detailed explanations of the universe's evolution from its earliest moments after the Big Bang. They've also discovered that our universe is expanding at an accelerating rate, although we're still unsure about what's causing this acceleration.